Hello, everybody. I'm Shinichiro Kawasaki. Today, I'm speaking from Japan. I work as a research engineer at an HDD development site in Japan. I have a career background about HDD technology and Java technologies. Now I'm working in a research team, and zoned block device is the current research theme. It is a bit sorrow that we cannot have face-to-face presentation, but this virtual conference is also the great way of communication, I think. It is my big pleasure to have a chance to present in this great conference. I appreciate all of the efforts to make this conference happen. My presentation title is Zoned Block Device Support in Hadoop HDFS. This is the agenda of this presentation. Let's start with the background story. In this conference, there are a number of sessions about zoned block devices. It is better to avoid repetition of zoned block device explanations, but let me touch it briefly. If you need the detailed explanation about zoned block devices, please refer other presentations. The zoned block device is the new class of storage devices, which increases capacity and performance. Especially, it increases capacity and then it reduces the storage cost. Regarding the HDD, as areal density grows up, the data tracks gets narrower and narrower. And at last, we need to allow them to overlap. This is the SMR, Shingled Magnetic Recording technology. And to allow this overlap, the write to the track must happen in a sequential manner. With similarity, NAND memory or SSD can have cost benefit by the sequential write requirement. How big the capacity increase benefit is. As an example, let's say one HDD has 12 terabyte capacity with the conventional recording method. Using this exactly same hardware and mechanics, that HDD can have 15 terabyte capacity. It means that this one HDD can have 3 terabyte capacity bonus as the benefit of the zoned block devices. This is the cost benefit of the zoned block devices. Instead of the benefit, zoned block devices have the restriction. It can do random reads, but writes must be sequential. Each device is divided into zones. Each zone has large size. For HDD, its typical size is 256 megabytes. There are two types of zones: conventional zones and sequential write required zones. The conventional zones behaves as same as the regular non-zoned block devices, and it does not have cost benefit. The sequential write required zones is the area with cost benefit. But for these zones, writes must be issued sequentially, starting from the zone write pointer. Write pointer is positioned at zone start at the beginning, and as data write to the zone go forward, the write pointer moves forward. And every write to this zone must happen at this write pointer position. When we need to erase the data in the zone must be reset beforehand. When it is reset, all the data in the zone is lost. These are the sequential write restrictions. In contrast to these write operation restrictions, read operations has no restriction. Read can be done at random position. This contrast, restricted write and no restriction to read, implies that write once, read many is the suitable usage of the zoned block devices. This zone and its behavior are defined as standards. For HDD, ZBC and ZAC are defined, and for NVMe, zoned namespace, ZNS, is defined. Following these standards, Linux abstracts it and then supports zoned block devices. To support zoned block devices, an effort has been made to the Linux ecosystem in the past several years. From driver layer, block layer, device mapper, file systems, and to the user space libraries, all of these now support zoned block devices. To make the applications enjoy the benefit of the zoned block devices, the applications need to follow the sequential write restrictions. There are two approaches to do it. One of them is to handle by lower layers. The file systems such as F2FS or BADAFS or device mapper DM zones support zoned block devices. Using these, applications can use zoned block devices as if they are the regular non-zoned block devices. With this approach, applications need no modification. However, this approach has performance overhead. The other approach is to modify the applications to follow sequential write requirements. Using the user space libraries such as libzbc or libnvme, or using the simple file system zonefs, applications can operate zones on zoned block devices. The applications can do zone write at desired timing with desired size. With this cost of the modification, the performance can be more effective, especially if the application already writes data sequentially. The application is the very good target to utilize zoned block devices. LocksDB and LevelDB are such an application with sequential writes. The other example of such an application is Hadoop HDFS that we are going to discuss today. As you know, Hadoop is the famous framework for distributed mass data processing. It allows processing target data size to scale up. HDFS, or Hadoop Distributed File System, is a file system designed for Hadoop. HDFS has name node to control the whole data in HDFS. It also has many data nodes with storage. HDFS can have data nodes with storage as many as we want to support scalable data size. This data node has big storage, and it means that it has certain amount of cost is paid for the data node storage. The zoned block device has potential to reduce this data node storage cost. One of the key HDFS design is that it targets large dataset. Gigabytes or terabytes file size is assumed for HDFS use cases. And the other key design is that it assumes write once, read many semantics. These design points have the high affinity with zoned block device. Please remember that the zones have large size, such as 256 megabytes, and the write restrictions on zoned block devices fits with this write once, read many semantics. This indicates that HDFS can support zoned block devices with efficiency. Based on this idea, I have modified HDFS to support zoned block devices. Let's see how it can be supported. To support zoned block devices with efficiency, HDFS needs modifications, but those modifications should be as small as possible. To minimize the changes, zonefs helps a lot. Zonefs is the simple file system for zoned block devices. Linux kernel supports it since its version 5.6. ZoneFS exposes each zone as a file. The operations to zones are mapped to file information and system calls. For example, when application wants to know the right pointer position, it can be done by checking the file size. To write the data to the zone, it can be done by file append write with direct I/O. To erase the data, zone reset can be done through file truncate system call. Such in-file operations are very easy to implement in user space applications. Many of these file operations can be done even through Java Standard API. This is very effective for HDFS, since HDFS is written in Java language. HDFS handles data on DataNodes as HDFS block files. To utilize zonefs, these HDFS block files are mapped to zonefs files using symbolic link. With this approach, many of the existing HDFS Java code can be used as is to handle HDFS data in zonefs files. However, still some more modification is required in HDFS. Those changes are related to direct I/O. In usual, file write is done as buffered I/O. Write requests are buffered in memory pages by file systems. The buffered data in pages are written back to the drives later. If data is written to zonefs files as buffered write, data write from page to drives are not guaranteed to be sequential. Then it cannot fulfill the zoned block device sequential write requirements. In contrast to buffered write, direct writes go directly from the application to the storage device. So when application makes sequential write requests, those are passed to device as sequential writes. To ensure the sequential writes, zonefs prevents buffered write and only accepts direct writes. In the next page, we discuss how this direct I/O write affects zoned block device support in HDFS. There are three problems about direct I/O write. First problem is that the zone files must be opened with ODirect flag. However, Java Standard File Open does not support it at its version 8. File Open for Direct I/O was supported with Java version 10. The Hadoop HDFS still must be built with JDK version 8. Then file open with direct I/O cannot be done. How to specify all direct flags at file open? This is the first problem. The second problem is memory address alignment. The direct I/O requires memory with write data to have starting address aligned to the device physical sector size. The Java memory allocation does not support it. How to align write data buffer address? This is the second problem. The third problem is about the data size. All writes to the zonefs files must be multiple of the device physical sector size, since sector is the unit of the data write to zones. On the other hand, HDFS block files can have any size with byte unit. So when we store the HDFS block files to zonefs files, there is some remainder which cannot be stored. This chart visualizes it. This green part shows the data are stored in a zonefs file. It has unit of the sectors. On the other hand, HDFS block file can have any size in byte units. So this purple part shows the remainder which cannot be saved in the zonefs file. How to handle this sector remainder? That's the third problem. These problems can be addressed with three solutions. As for the first problem, HDFS already has a special way to open files with special flags. Using this, a new Java method can be implemented to support all direct flag at file open. As for the second problem, a new JNI method can be implemented. It allocates the aligned starting address. Write data in Java byte buffer is copied to this aligned buffer, then passed to write system call. Regarding the third problem, the sector remainder can be kept in the memory. During the write operation, this sector remainder is kept on the memory, and when the write stream of the block file is closed, this remainder data on memory is saved on the disk. When HDFS reboots, this saved remainder data is read back into the memory. With these solutions, I modified HDFS DataNode codes. This chart shows the changes made in the HDFS DataNode. DataNode has many classes. When HDFS operates block files, those operations are always passed to the class File IO Provider. This File IO Provider adds hooks to file operations. Those hooks are used for performance measurements and failure injections for testing. In other words, this class wraps around all of the file operations. This wrap-up design can be reused for zonefs support. Zonefs files require its unique operations. To hide those uniqueness, I added the new class zonefs File IO Provider, which extends File IO Provider class. This zonefs File IO Provider overrides these methods to implement zonefs unique file operations. These methods use other new classes such as zonefs, zone, or zone writer. This approach hides the uniqueness of zonefs files and then reduces the impacts to DataNode classes. With this approach, still, 8 existing classes needed changes. Native I/O class needed changes for new methods, for file open with ODirect flag, and JNI method for memory address alignment. File I/O provider class needed a few interface changes to fulfill the zonefs file I/O provider requirements. This file I/O provider interface change affected several classes in the DataNodes. In total, 1.5K lines are added to HDFS to support zonefs. HDFS itself has 1 mega lines code, so comparing this number, I can say this 1.5K lines addition is a rather small changes. With the changes I explained so far, HDFS block files can be written and read using the zonefs files. From file data I/O point of view, zoned block device support is already achieved. However, from the performance point of view, another change is required in HDFS. When DataNode receives block file write streams in parallel, the receiver threads write to multiple zone files, and then it results in the performance degradation. Let's say the DataNode receives 2 write streams. This receiver thread receives 1 write stream and then write to this zone number 1. The other receiver threads receives another write stream and then write to this zone 2. When this happens in parallel, these 2 threads receive and write data packets alternately, one after another. First packet is written to this zone 1, second packet to this zone 2, third packet to zone 1, and fourth packet to zone 2, fifth zone 1, and sixth zone 2. This results in non-sequential writes across zones. It still does not cause write failure, since writes to each zone is sequential. But this non-sequential write across zones causes throughput degradation. To address it, I took an experimental solution. It makes the receiver thread to buffer whole data to write to a zone, and then after that, it kickstarts this writer thread. With this approach, the write to these 2 zones are not in parallel. Firstly, zone 1 is written, and then after that, data is written to zone 2. With this approach, the throughput degradation can be avoided. This is still an experimental solution. The whole zone data buffering is not ideal. since it needs rather large memory size. Further work is now ongoing for improvements. Using the modified HDFS, I built up the HDFS system and did performance evaluation. Let's see the performance evaluation results. This page lists up the setup of the evaluation system. Total number of the servers is 5. Each server has 10-core CPU and 64 GB DRAM. These 5 servers are connected with 10 gigabit Ethernet. 3 of the servers are DataNodes. Each of the DataNodes has 2 HDDs. One HDD is SMR, Shingled Magnetic Recording HDD, as the zoned block devices. The other HDD is CMR, Conventional Magnetic Recording Storage, for comparison. These two HDDs have different capacity but have identical mechanics. So raw I/O performance is the same for these two HDDs. HDFS is configured to have 3 replicas. The size of HDFS block file is set to 256 megabytes. This is same as the SMR HDD zone size. For Hadoop and HDFS, I used the latest release 3.3.0. For operating system, I used latest Fedora 32 and the stable kernel 5.7. To understand the performance of zonefs on top of SMR HDD, I compared performance with other file systems and CMR HDD. This table lists up the 5 different setups of DataNode. ZoneFS is compared with other file systems used for mass storage, such as ext4, XFS, and ButterFS. ext4 and XFS on CMR HDDs. This is the usual setups for HDFS and Hadoop. As for ButterFS, I compared it both on SMR HDD and CMR HDD. Please note that the ButterFS SMR support is a prototype, and now work is ongoing for mainlining. I used 2 benchmarks for evaluation, DFSIO and Tera Sort. Firstly, let's see the numbers measured with DFSIO. DFSIO is one of the major benchmarks which runs on Hadoop and HDFS. It evaluates HDFS file I/O throughput. In this page, these 2 charts show the DFSIO results, which measure the write and read throughput of a single file with size 128 gigabytes. The OS page cache was flashed after write benchmark run and before read benchmark run. Then this read benchmark result does not reflect buffered I/O benefit. Regarding the write speed, file system with buffered write shows a better throughput. XFS, ext4, and ButterFS can do buffered I/O on CMR HDDs. ZoneFS requires direct I/O, then it shows slightly slower throughput. Regarding the read speed, ButterFS on CMR drive shows the highest performance. ZoneFS on SMR drives shows the second performance, and it is better than ext4 and XFS on CMR drives. When we compared SMR drive performance between ZoneFS and ButterFS, ZoneFS provides the highest performance for both of write and read benchmarks. This indicates that write restrictions handled in application layer has lower overhead than the restriction handling in lower layer. As the next step, I measured parallel I/O throughput. DFSIO can measure throughput of multiple number of files. This chart shows the write throughput changes from single file to 4 files. We can see that as number of parallel write stream increases, the write throughput decreases. With 2 streams, the throughput becomes half of the single write stream, and with 3 streams, the throughput is almost 1/3. The red line shows the throughput of ZoneFS on SMR. This ZoneFS throughput is comparable to with other file systems on CMR drives, such as ext4 or XFS. ButterFS on CMR shows the best throughput. Please note that this ZoneFS result reflects the writer threads. As I noted before, without the writer threads, ZoneFS has overhead by non-sequential writes across the zones. With these writer threads, ZoneFS on SMR throughput is comparable to other file systems on CMR. This chart shows the parallel read throughput changes by number of read streams. This red line shows the throughput of ZoneFS on SMR. Even though the number of read stream increases, the throughput does not change up to 3 streams. This is because the workloads are assigned to 3 data nodes, which has 3 replica. The file reads requests to each file is assigned to each data node. Then there is no performance degradation. Comparing with ZoneFS, ButterFS on CMR shows a better performance. On the other hand, ext4 and XFS on CMR have rather lower throughput. This is because the data was not written sequentially, then data read was not sequential either. This resulted in the gap between these file systems and zonefs on SMR. Let's see the application benchmark Tera Sort result. Tera Sort is the basic benchmark of Hadoop. It measures time duration spent on large data sorting. It has 3 steps. The first step is TeraGen, which generates the data to sort. The second step is Tera Sort, which does data sorting. And the last step is Tera Validate, which checks the sort results. This page shows 3 charts corresponding to those 3 steps: TeraGen, Tera Sort, and Tera Validate. This benchmark was run with 128 GB sort data. Please note that the lower is the better for the numbers in this page. The result of TeraGen showed that CMR HDDs have better performance than zonefs on SMR. This workload generates data and writes it to HDFS files. Then write throughput affects this TeraGen result. This result is consistent with DFSIO write benchmark, which showed good performance with CMR HDD. As for Tera Sort, performance is comparable across all file systems and CMR SMR HDDs. This workload does sorting with CPU, and HDFS file I/O is not the key factor. Then it results in the almost same numbers across file systems. Regarding the Tera Validate, zonefs on SMR gives the highest performance. This workload reads out sort results from HDFS files, then read performance is the key factor. Again, this result is consistent with DFSIO, or read benchmark result. It indicates that zonefs and SMR HDD are good at read operations. When we look at SMR HDD results of TeraGen and Tera Validate, zonefs shows the better performance than ButterFS. This also is consistent with DFSIO results. It's time to wrap up this presentation. There are 2 conclusions. First one is that zoned block devices can be supported in HDFS with 1.5K line changes using zonefs. Zonefs allows zone operations through files. Then it reduces the code changes in HDFS. Also, this is the approach not to rely on lower layers to handle zoned block device write restrictions. Then it has lower overhead. The second conclusion is that file I/O performance of zonefs on SMR drives is comparable to other file systems on CMR drives. Especially, read performance is better than ext4 and XFS on CMR drives. It was also confirmed that zonefs results in better performance than ButterFS on SMR drives. This proves that zonefs has a lower overhead than zoned block device handling in lower layer. Today, I have shared current status of this project. This project is now in progress, and as it goes forward, 3 works will be required. First work is evaluation with larger system. The performance evaluation shared today was done with 3 data nodes. This is rather small number. Evaluation with more data nodes and larger data size is required to check the stability and performance of the approach. We will plan to evaluate with petabyte scale dataset. The next work is the writer threads. As I noted, current implementation of the writer thread is an experimental one. Especially, write buffer memory size needs reduction. After the improvements, the third work to do will be code change proposal to Hadoop project. Hadoop and HDFS are the open source software supported by the community. To convey the zoned block device benefit to the HDFS users, this work will be important. It's all about my presentation today. Thank you very much for listening.